Okay, so this is the first of two lectures on a subject called dimensional analysis, and what we're interested in is how to use the dimensions of our variables to simplify our analysis and how to educate us in terms of how to scale an experiment. So for instance, if you wanted to work out the drag on an airship, it's an expensive business. You've got to build an airship, you've got to put an engine on it and work out how much fuel is being consumed as it moves. So what you prefer to do is you prefer to build a small airship that you could fit in a wind tunnel in your laboratory, make some measurements, make some calculations, and then apply those calculations to a real scale thing, so you'll be reasonably sure that your airship is well powered. So you can do this, and you do this by considering the variables that are present and grouping them into non-dimensional groups. And these non-dimensional groups are absolutely fundamental to understanding what type of physics we've got in our particular problem, and they are extremely important. That you'll make much more use of them in future years than you will in this particular module. So we've got our governing equations of mass, momentum and energy. So this is density and velocity and specific energy, and these variables have different units, so kilograms and meters per second and joules per kilogram. And we already know in this module that we've got variables with lots of other quantities as well. So we've got things like force, we've got acceleration, we've got thermal conductivity, we've got energy, and so on. And the way we deal with this, and the way we kind of parameterize this problem, is we say, well, we've got some master or some fundamental dimensions, and we're going to build all of our other variables out of these master building blocks. So effectively for this module we say there are three. There are mass and length and time, and we can build any of our other, if you like, higher variables out of this particular master set. And this gives you an example. So for any variable we're going to have a certain number of masses, a certain number of lengths and a certain number of times, and that will define our general variable. So a good example is velocity. It's a certain when you move a certain amount of distance in a certain amount of time, you have a certain velocity. So it's length and time to the minus one. And then acceleration is the next step from that. That's the rate of change of velocity with time. So it's length per time per time. And force is mass times acceleration. So it's mlt to the minus 2, and so on. So we can do this with all variables. And this is also very useful to make sure an equation is consistent. So there are two reasons why you want to do this. The first one is, let's say you've got some variable and you can't actually remember what the dimensions are. So in that case, if you can remember an equation, you can work out what's left of the variables that you do know. So for instance, let's say we know that pressure is equal to the gauge pressure and it's equal to rho gh. And let's say, for instance, we can't remember what the dimensions for pressure are, but we can remember what these things are. And so this equation is dimensionally consistent in the sense that its a pressure is equal to another pressure. And it's just in this different form. So, and we can work out the dimensions of density, so that's mass per unit volume, so that's this bit. And then we've got acceleration, that's our length and time to the minus 2, and we've got one length, which is our h. So this gives me, this is my master dimension of pressure. And if you think about this, this makes sense because we know that force is mlt to the minus 2, and we know that pressure is force divided by area. And we've got L to the minus 1 here, so that's 2 less lengths than we've got up here. So this seems to be correct. The other reason why this is very, very useful is particularly relevant to answering exam questions. So when you derive an equation, effectively you come up with something like this, and it's got to be dimensionally consistent. You've got to have all of these things equaling the same variable. So this is a great way to check that you're when you've done your derivation, you've done it and you haven't forgotten to square a variable or somewhere along the line. Okay. So dimensions are not scales. So dimensions tell you what the variable is, and the units tell you how much of it there are. So if I draw this little sketch like this, I've got an object, certain length scale, length dimension, and it's got a flow going over it, and there's a certain drag on it. But I don't know, because I haven't said how big this thing is. So this could be a micron, or this could be a meter, and there's no scale associated with this. Okay, so the units are the things that define the scale, and in this module we're going to be working in SI units only. So the units that you're going to be using are relatively straightforward, because they're always powers of 10 of one sort or another. And just as I mentioned in the 2 slides ago, when you're deriving equations, it's a great way to make sure you haven't made any errors in your derivations. So when you derive an equation, if you have a term and another term and another term, they've all got to be the same thing. You can't say that a velocity equals a pressure plus a length minus an acceleration. And if you derive your equation correctly, you will have all of your terms must have the same set of dimensions. So if you've derived this equation, for instance, you can check that your left-hand side and your right-hand side all have the same terms, and if all of your terms are dimensionally consistent, you can be reasonably sure you haven't made any sort of algebraic slip-ups when you've been deriving your equation. And this is a key thing to do every time that you do a derivation. And don't just apply it to this module, do this for every single module and every single exam question where you do a derivation, because you will be surprised how many mistakes you make in the sort of the heat of the moment. Okay, so let's sort of get onto the practical end of this lecture. And one of the important things that we can do with dimensional analysis is we can use it to do 2 things. We can use it to make our experiments easier, and we can use it to parameter or to make sure that lots of different experiments can be plotted so that they all match up, and you can get data from one set of experiments to your particular need. So let's discuss both of those things very briefly. So let's say I've got an airship, it's 100 meters long, it's 10 meters wide. I want to work out how big an engine I need to put on it, and to do that I need to work out the drag on the airship. So let's say this thing here is my airship. It has a certain diameter, length scale, so we'll call that L, and it's going to go at a certain speed, so that's the velocity, and there's going to be a certain amount of drag on it. So that's this D, and it's going to be going through air, so air has a particular density and it has a particular viscosity. So my question is, well, how does my drag depend on the size of my airship and the velocity I want to go and the fluid through which that I'm going to make it move? So I can say quite specifically that my drag depends on, or is a function of, these 4 variables. So if I was going to do an experiment, I would want the one way to do it, which would be the stupid way, would be to do an experiment with an airship of different sizes and different velocities and different densities and different viscosities, and I'd end up having to do an awful lot of experiments. So let's say I might want to change the length by 3 or 4 times, and the velocities by 3 or 4 times, and the density by 2 or 3 magnitudes, and the viscosity by a little bit as well. That's when you multiply all of these things together, it's an enormous number of tests. So one of the things that dimensional analysis allows us to do is to convert this 4-dimensional test problem to a 1-dimensional test problem. So we only have to actually test one parameter on the right hand side rather than these 4. So that saves us a huge amount of time. And it turns out that this parameter is non-dimensional, and what this allows us to do is when we get our results, we plot it in a non-dimensional way. So my y-axis has no dimensions and my x-axis has no dimensions, and this allows me to plot experiments that I used completely different fluids on the same figure, and make that data useful. So for instance, it might be that there are some results in the literature somewhere where somebody's done some experiments, not in air, but in water, on a kind of an airship shaped thing, and it might be that the non-dimensional parameter in their experiment is very similar to my particular airship that's going to be in air. And we'll talk a little bit more about this at the end of the lecture. Okay, so how do we go about coming up with our single key parameter? So the first step we do is we take our functional relationship, so that's this thing here. So this, in words, just says my drag depends on length and velocity, density and viscosity in some way. I don't know what it is, but I know that it depends on these 4 variables. Okay, and I know the dimensions of each of my 4 variables. Okay, I've got length, velocity, density and viscosity. Okay, and so the first thing I do is I take some of these variables that I know drag depends on, and I combine them in a clever way such that the dimensions of my selected variables matches up with my dimensions for drag, which is this thing up here. Okay, so it turns out if I use 1 density, 2 lengths and 2 velocities, and I put them together, I come up with this magical result that the dimensions of these 3 variables taken together is the same as the dimensions of drag. And then what I do is I say, well, okay, I've got this group of variables, so I'm going to divide the left-hand side and the right-hand side of this equation by rho L squared U squared. Okay, so that's fair enough, I can do that. So here we are, I've done this, and this is my drag, but the key thing is this has no dimensions. So this equation had effectively a drag dimension. This said drag equals some function of L and U and rho, but it must be whatever terms I have here, they must have units of Newton, because it's newtons on the left hand side and I must have newtons on the right hand side. This equation is exactly the same, but it has no dimensions. So there's no dimensions here. So drag in newtons divided by rho L squared U squared has no dimensions. And I've still got some function over here, which I don't know what it is, but it's a slightly different function because I've divided by rho L squared U squared. So I'm going to use this G, and all this G is just it's just a different letter to F. So F is, all that F is saying that drag is some function of these 4 variables, and this G is just saying, well, this is another function of these 4 variables, but it's a different one to the one up here because this one must be non-dimensional and this one has units of drag. Okay, so in the next lecture I tell you how to get this, because this is quite key, but I'm going to skip over this for this particular lecture because I want to just get across the main message without getting muddled up with maths. Okay, so we've gone from here to here. We haven't changed the physics, we've just changed the look of the equation. It's now a non-dimensional functional equation. Okay, so now we've got to make the right-hand side of our equation non-dimensional, because the left-hand side of our equation is non-dimensional, and it's an equation, so whatever terms we have in our equation, they've all got to have the same dimension. And we know for sure that the left-hand side is non-dimensional, so the right-hand side must be non-dimensional as well. And so effectively what I've got to do is I've got to make my right-hand side non-dimensional. So what I did was I took some L's and some U's and some rows, and I used that to make the right-hand side non-dimensional. So what I ought to do is I ought to start off with the viscosity, because this is the one thing I haven't used, and then what I need to do is I need to take a couple of L's and a couple of U's and a couple of rows, and I need to combine them in a certain way such that I make sure that the dimensionality of my viscosity disappears, and I make a collection of variables that are non-dimensional, and then my equation is consistent. Okay, so and it turns out if I have one density and one length and one velocity, one length, one velocity, one density, it turns out that this has the same dimensions as mu. So if I take this group of variables and divide by mu, or if I have mu and divide it by rho ul, I end up with a non-dimensional group. Okay, so now what I've got is I'm saying that the non-dimensional group drag depends on only one group of variables. Okay, so this is quite interesting because I've changed my four-dimensional design test problem to a one-dimensional test problem. So I don't have to test against length and velocity and density and viscosity separately. I just have to test against this group of variables on its own. So this group of variables is pretty key. It's called the Reynolds number. It's the most famous non-dimensional number that you're going to come across in thermofluids. And it effectively defines the transition between a laminar flow and a turbulent flow. If you remember the lab that you did back in week 1 or week 2, you had a dye in a channel, and when you turn the flow up, the dye sort of became chaotic and diffusive, and it disappeared. That's when the Reynolds number went beyond a critical value, and you went from a laminar to a turbulent flow. And this transition between laminar and turbulent flow is really important when you start working out the drag. Okay, so we've got our non-dimensional relationship, and we've made our design test problem much, much easier because we now have one key parameter that our drag depends on rather than 4 of them. And this is just an example of how the Reynolds number affects the flow around your object. So we're still thinking about airships, so let's imagine that this is an airship, and when the Reynolds number is really, really low, you have nice ordered flow, it's called creeping flow around this object. It's symmetrical fore and aft, and there's no separation. And when the Reynolds number goes up a little bit, it's still laminar flow. So you can see laminar flow because you've got these nice lines, so you've got fluid particles are flowing down these lines, and you get separation at a point here and a separation at a point here, and you get this kind of recirculation region that's going on inside it, and you get this separation. And the drag characteristic of this thing and this thing is completely different. And when you turn the flow up, so the Reynolds number goes up, the separation point moves around a bit more to here, and you get a much bigger separation region here, and this wake becomes unsteady, and this wake kind of becomes turbulent. Okay, and the drag characteristic of these three things is completely different, and it depends totally on the Reynolds number. Okay, so in this example, what's going on is, let's say our length is constant. So let's just imagine, for the sake of argument, the width of this and the width of this and the width of this is the same. And the obvious thing to do to increase the Reynolds number is to increase the velocity. So we're going from here to here to here. But I just want you to think about the Reynolds number, and we could also do this by changing the viscosity. So let's say, for instance, we keep the velocity the same, and we keep the length scale the same, and we keep the density of the fluid the same, but we reduce the viscosity. So this is like going from treacle to water to air. With the same thing and the same velocity, you'd still get the same change in the flow around the object. You still get the same flow patterns. So you can change the Reynolds number in different ways, but as long as you change it to the same value each time, you'll get the same flow patterns behind it. And this is the key thing to think about when you want to go from a model to a real scale and back again. If you can keep the Reynolds number the same, you'll get the same physics. And this is how you can go from real scale to model scale in the lab. Okay, so thinking about this, if we wanted, this is my airship, and the Reynolds number on my airship, and let's say I want to go from my airship to a laboratory scale model. So I might want to reduce my L in my airship down to something I can fit in my wind tunnel, so maybe 10 or 20 centimeters, and I might want to reduce my flow speed in real life from, say, 1 meter a second down to 0.1. So if I can do that, so I know what my U airship and my L airship are, and my U model and my L model are, and I know that my airship is going to be moving in air, so the density and the viscosity are fixed. So this means I can do this and choose a fluid that is going to run in my tunnel. So I might not have to I might not be able to use an air tunnel. I might need to use a water tunnel, for instance. And if you can do this correctly, you can match the real scale to the model scale, and then you can do the measurements. And you can do this for the Reynolds number matching, and you can also do it for the drag coefficient matching. So when you do your model drag measurements, you can then convert it back to what your real scale drag measurements would be, using exactly the same procedure. Okay? So the one thing we're not able to do with this is to actually work out how the drag depends on the Reynolds number. So to do that, we have to do experiments, or we have to do some computer simulation. So to work out what this functional relationship is, so if I flick back a couple of slides, effectively, what is this H? How does my non-dimensional drag depend on my Reynolds number? Well, for that we have to do some experiments, and if you see it on a curve, so this is a non-dimensional plot, this CD is my non-dimensional drag, and this is my Reynolds number. So this is a non-dimensional plot. I've got no dimensions on my x-axis, I've got no dimensions on my y-axis, and this curve, this is my functional relationship for this particular shape. Okay, don't worry about these other ones yet. We're going to talk about those right at the end of the module. And also don't worry about this particular shape and why it does this. We will talk about this in great detail when we start talking about boundary layers and viscous flow towards the end of this module. Okay, but this line, this is my functional relationship. This is my H of Reynolds number, and we only can get this by doing some experiments. Okay, so when you read textbooks, on fluid mechanics, you'll see lots of plots that are non-dimensional. So if I do a model of something in a water tunnel at a certain Reynolds number and I measure the drag, I can plot my non-dimensional results like this, and then somebody can come along who wanted to build an airship. They can go, well, I think the Reynolds number of my airship is such and such a value, it's this one, so I can work out my non-dimensional drag, and I know what my velocity and my length and my density are for my particular airship. So using that information, I can actually work out my actual dimensional drag for my airship from this non-dimensional plot. And that's why non-dimensional numbers are really, really useful in engineering. Okay, so we've done quite a lot here. We know what a dimensional unit is. We know how to save marks in exams by checking dimensional homogeneity. We've been introduced to non-dimensional groups, and we see their importance in terms of how we're going to use them to go from real scale to model scale. We're not quite sure how we came up with these non-dimensional groups, and we're going to cover that in great detail in the next lecture. And I will deal with this worked solution in the next lecture as well. Okay.